All right, this is my second video where we're going to be calculating the weighted averages for the atomic masses of elements. Okay, I want to take a look at the first one with you because some of you might be wondering about relative abundance. And here you're not just given the relative abundance, you have to figure it out. And that's not hard to do, it's very simple. You have a total number of lithium atoms here. You have 400 lithium atoms. But 30 of those atoms are lithium 6, and 370 atoms are lithium 7. So we need to find the relative abundance in percentages. We're going to take 30 divided by 400 and 370 divided by 400 to get the relative abundances. All right, so I worked out the relative abundances. Lithium 6 is 7.5%, and lithium 7 is 92.5%. And now we can calculate the atomic mass for lithium. Now, here's another fold to this. You're probably noticing that we're given numbers in grams per mole. You have no idea what grams per mole is yet, and you shouldn't, and you don't have to. We're just going to use this number as AMU, and you don't have to worry about it whatsoever. We're just going to go with 6.015 AMU and 6.016 AMU. And there you have it. Taking the weighted average, we get 6.941 AMU, which is exactly what we find for lithium on the periodic table. Okay, let's try number 3. There's a little interesting fold to number 3. In this case, you're given the mass, the atomic mass of copper 63. And copper has 2 naturally occurring isotopes. What is the atomic mass for the second isotope? Okay, so we're going to have to put a little bit of thought into this, but basically we're going to follow the same procedure, i.e. equation that we were following before. I'm going to set that up and then we can talk through this, okay? Here we go. All right, so I've set this up. Let's see why I did what I did or where I got these numbers from. Okay, so like we've done before, we're finding the weighted average. How did we do that? Well, we would take the mass times the relative abundance plus the other isotope, take the mass, which now is X, times the relative abundance. Where did I get this number? This relative abundance is simply 69.15 minus 100. Well, a positive number. So we've got 0.6915 and 0.3085. Now we just really need to solve for X. Okay, so again, and where did I find this number? I went to the periodic table and I found the weighted average for the atomic mass of copper. Okay, all I'm going to do now is solve for X. So I'll do that in a couple steps so you can see what I did. All right, so I solved for X. I think what I did was pretty obvious, just using simple algebra. Solve for X. So what is the atomic mass of the second isotope? It is 64.30 AMU. All right. Okay. The most difficult problem in this entire problem set is really number 7, in my opinion. And I think we'll work through this. Okay. I think we should do this. I'm going to set this up as we set up the previous one, only this time we've got 3 isotopes, And for two of the isotopes, we don't know the percent abundance. We have to find the percent abundances for those two isotopes. So let's give this a try. I'm going to set it up. Okay, I set this up. This is the average atomic mass for for neon. Okay, this is going to represent isotope number 20. This is going to represent isotope 21, and this is going to represent isotope 22. Okay, here we're taking the mass. Now, this is the mass number again, but this is the best information that we're given, so we're going to use the mass number since we're not given the actual atomic mass. So we're going to take 20 times the relative abundance, and we're going to take 21 times the relative abundance of 21, which is X, and the relative abundance of 22, which is Y. Okay. All right, so you should recognize that if I take 0.905 plus the relative abundance, which is X, and the relative abundance, which is Y, relative abundance of the isotope 21 and the relative abundance of isotope 22. If I take 0.905 plus the X value plus the Y value, I should get a total of 1, right? So what I'm going to do now is solve for Y here. Okay, so that's 0.095 equals X plus Y. I'm going to solve for Y now. All right, so Y equals 0.095 minus X. So what I'm going to do now is I'm going to take this value for Y and substitute it up here. So I'm going to rewrite this. So that's what I did. I substituted this value for Y. And now let's simplify this equation. All right, so I did all the work here, and I really would leave it up to you, I guess, to follow the algebra that I did here. Really, I came out with an X value for the for neon 21. X is the relative abundance of neon 21. I got 1%, and if I follow this equation here to find the relative abundance for Y, I take 0.095 minus my X value, and I get my Y value, which is 8.5%, which is neon 21. I mean neon 22. Now, I think it makes sense to check my math here. You know, I want to make sure that, you know, this answer is right. How can I know that? Let's go back to this and plug in my numbers. Actually, what we want is this way up here. So I'm gonna work through that equation and see if I get 20.18. So here we go. All right, so it all worked out. I got my answer, which is 20.18 AMU, and in fact, that is the atomic mass for neon that was given. So we did it right. All right, guys, I hope that was helpful. I'll see you next time.